tool is a calculator that came out for 241, and then how we think it's going to evolve in this, and then we'll talk about some Q&A. But first of all, and there's a number of slides in here that take the engineer's perspective into consideration. And then, just first point, during the pandemic, there was a lot of urgency. Public health officials were giving us some misleading or changing information. And the question that's all, that we're asking right now is how did we do in responding to the commercial and the customer demand about doing something to improve the air quality? As designers, you didn't have a lot of information to trade on. This was the first time we had seen a situation like this before. We knew HEPA filtration was very effective in healthcare applications, but we didn't really know, especially early on, how the virus was moving in the buildings. How was it being transmitted? And now we know a lot more. The CDC has come out with positions on this, and so has the World Health Organization, and now ASHRAE has. And so the one thing I can tell you is we may not know how well we did in answering the customer's question of helping me mitigate the risk, but through 241 now and going forward, we now have a better way to evaluate the likelihood of that product being successful. And so there's two very important terms in Standard 241. Number one is the Infection Risk Management Mode, or IRMM. So what is this? This is a definition of how a building should be managed in the case of another outbreak. And so if the public health officials or some AHJ says, hey, we have a high risk of infection, I would like your building to go into an IRMM, or infection risk management mode, you have to have a defined protocol for what to do during that situation. And infection risk management comes in the form of two things. You'll see it in a second: reducing the number of people in the building or increasing the amount of equivalent clean air. So if you think of it as a balancing act, I can take people out of the space to reduce the amount of virus that gets delivered and or potentially gets absorbed by the people. And then the other way to do it is increase the air cleaning while keeping the population the same and making sure that the air that's exchanged in the building is clean, okay, or cleaner. So that's what an IRMM is all about. And the fundamental math behind the IRMM is how much equivalent clean airflow you need, which is expressed on a per person unit, a unitary basis, how much equivalent clean airflow you need to reduce the risks. The three components, and this is actually pretty straightforward if you think about it, the three components to clean air are how much outdoor air you have available, how much air is being disinfected by the cleaners, the air cleaners that are in the space, and how much filtered and recirculated air through a good filter is available. Those three things come together to deliver an equivalency of clean air. And equivalent to what? It's really, in ASHRAE's terms, it's equivalent to bringing in outdoor air. Okay, so everything in this standard, outdoor air, air cleaned by an air cleaner, and filtered recirculated air is equivalent when it comes to reducing the risk of infectious aerosol spread, which is pretty exciting. This is the first time there's really been an equivalency for these types of controls. So you'll see real quick the point ASHRAE was trying to make about the standard. And in the end, it says in the foreword of the standard, it says, ultimately, this work, all of this technology evaluation that goes on here, will enable more widespread and confident adoption of these technologies, which are air cleaning technologies, which is precisely what we as engineers, we as product developers, I think as end users, want to know is, hey, things have changed, right? We know indoor air quality matters. There's a lot more that we've learned about since the pandemic. It may not be about virus spread all the time, but as we become more sensitive to air quality, what should we do and how should we apply it and what technology is effective? And now the standard emerges to help us evaluate that. It's a bit of a busy slide, but I wanted to bring it up because it's important. And that the first rule of thumb or the first requirement to apply ASHRAE 241 is that the building design needs to be in compliance with ASHRAE 62.1, 62.2, or 170 for ventilation rate. So number one, the assumption is you've done your work as an engineer, you've designed it to the ventilation rate procedure in 62.1 or 62.2, or the indoor air quality procedure, and you followed digressions of 170 for healthcare spaces to get your minimum ventilation in the space. Once you've met the minimum ventilation, you then layer on additional outdoor air, cleaned air, or filtered air through 241. Next important point is that air cleaners used under the standard or air cleaners evaluated for compliance to the standard must have been evaluated by an independent third-party lab for effectiveness, meaning how well does it remove particles from the air? And those tests are done in triplicate. And then how well does it work in the same setup around generation of byproducts? So what's the safety rating on the product? These are all defined in normative appendix A, and the tests are to a ANSI or AHAM or ASHRAE standard test. So third-party labs do this work. To give you guys a sense, it costs anywhere between $25,000 to $30,000 to engage with one of these labs and do this work per product. So it's a very costly endeavor, but it is obviously very worthwhile and something that we've invested in, and I think a lot of other manufacturers have, to bring this data forward to the industry. The standard method that is used here is that the device that's tested is then scaled for real world application and allows you to understand how much equivalent clean airflow that product generates. Okay, and so that's the whole point, right? So I'm trying to create more equivalent clean airflow in my space. So if I have an air cleaner that's evaluated, I need to know what the value is that it delivers to my space. The other point I'd make, and this is something that we get asked from engineers all the time, is, okay, so I understand maybe 241 is not a requirement for my territory. It's not the law of the land yet. So what? And what I would tell you and anyone else that asks me this is that the so what is that finally there's a standard around safety. So you as an engineer that's using an air cleaner on a project could at least say that the products that are approved for use on my project that meet the requirements for my program here need to have at least passed the safety portion of 241. So that raises the bar around the performance requirements. It also eliminates poor quality product from entering the project, and also makes sure that what's left on the job when you're finished with it is a safe piece of equipment. So here's your first kind of takeaway slide on the new content here. 241 introduces a new concept that's called equivalent clean airflow. The equivalent clean airflow math matters. We'll get into it in a minute. It matters when you're in the IRMM, which is the risk management mode. Equivalent clean air, or ECAI, and 241 are used as a supplement to the existing ventilation rate procedures or the indoor air quality procedures. Now, under the standard, there's a way to evaluate air cleaners for how well they work and how safe they are, meaning that they don't generate byproducts. And in the scope of the standard are soft ionization, hard ionization, UVC, photocatalytic oxidation, and all of these other air cleaning technologies must operate within the safety limits. And those safety limits are how much particle they generate, how much ozone they generate, and how much formaldehyde they create. So those are the three safety byproducts that are tested. And basically, the quick takeaway I'm going to ask all of you is, as you recommend air cleaners, what are you recommending, and do they meet these requirements? And we've reached quiz number 1. So Ryan, take it away.
All right, I'm going to pop the quiz question up here. As soon as I find my button. Polls. All right. Quiz question number 1 launched. For all the quiz questions, you're just picking one answer. Just click on it. If you're mulling it over, that's okay. Before I close it, I'll warn you. That way you can pick something. And then after you've chose your answer, feel free to type questions in the chat box for Audie, and we'll see if we can get those answered too.
I'll just wait one more second. I tried to answer it, Ryan. It says hosts and panelists cannot vote. I'm very sad. Thought I knew the answer.
You might have got it right. I don't know.
Yeah, appreciate it. All right, well, let's get moving. So let's talk about equivalent clean air and how to calculate how much you need. So as is always the case in these kinds of things with ASHRAE, there's a table. And so within the standard, there's this table on the right-hand side. It's pretty straightforward. And this is a per person piece of math. And so table 5.1 defines how much clean air is required according to the standard to minimize the risk of infectious aerosolized spread. So you take the number from the table times the number of people in the space, and that delivers the amount of volume of clean air you need. And so you can see on the side, so volume of equivalent clean air you need equals the amount of clean air defined per person times the number of people. Pretty straightforward. To be clear, the number is a pretty staggering number. If you look on the right-hand side, I usually pick on the classroom. example, education facilities, it says 40 CFM per person. Typical classroom design with the ventilation rate procedure would deliver somewhere between, call it 13 and 16 CFM per person. So you're starting at, let's call it 15 on average CFM per person. You're trying to get to 40 if you were trying to meet the requirements of the standard. That's a big step up, but there's a path. So we'll get into that in a second. Before this standard, I want to put this in context. Before this standard, 62.1, 62.2, or 170 really define an outdoor air requirement. Sometimes they touched on filtration. Sometimes they touched on equivalent sort of like air changes per hour, or you can back into that number through the math for different spaces. But in the end, they didn't really tackle air cleaners very effectively. UVC shows up in 241. It also shows up in 62.1, 62.2, and 170. But they also have this message about making sure no ozone or avoiding ozone generating products on your projects. And so there's misleading information, I would say, generally, or maybe somewhat confusing information generally in prior standards. In 241, it is very clear that they are talking about cleaners that are used effectively, that generate clean air, that are safe. And so we'll get into that. To put this in context around the ventilation rate procedure, this is just directional to make the point. I take that classroom. If you look at classroom age 9, it's underlined. 33 people, 13, if I follow the ventilation rate procedure to a T, 13 CFM per person. Sometimes we oversize a little bit for safety factor. That's fine. So that's why I said 13 to 15. 13 CFM per person. I said you need to get to 40 from the table. That's an additional 27 CFM of cleaned air per person. If you just thought about doing it with outdoor air exclusively, you can see on the right-hand side, it would cost, I said $2.50 per outdoor air for equipment purchase would lead to $2,000. This is just a rough rule of thumb. This is in no way a quotation. It's just a directional statement. But the whole point is you need to deliver a lot more clean air in the space to be effective. I noticed there's a question about, can I get the slides? The answer is yes. We'll share the slides after this. So where does clean air come from? This is the summary of clean air sources from the standard. It's figure 6.1. I don't want to spend a lot of time on this slide. It is a busy slide. It has an incredible calculation on it with a sigma. It feels very, very nerdy. But the point is, on the left-hand side, all of your outdoor air delivered through a DOAS unit or through unitary equipment is added in. So that's the outdoor air that feeds a single or multi-zone space. You add to it all the cleaned air, the volume of air cleaned by a system. So you see the VACS and all those stars. Those are all the places where you can have an air cleaner in your system, whether it's filtration, whether it's a dedicated air cleaner in the room, whether it's in the ceiling, it doesn't matter. But those systems scrub certain amounts of air. Those are where the volume of returned air comes in that gets cleaned, and then it delivers VACS, which is the volume of air cleaned by the system. Adding all of that together needs to be greater than, you see over here, the greater than or equal to the VECI, which we calculated from above. So the number for the classroom was 40. So you can see the filter plays a part, an air cleaner that may be in the classroom or in the system or permanently mounted in the space can play a part, plus the outdoor air plays a part. So maybe you can kind of start doing the math in your head. Okay, so I now need to come up with that 26 CFM. It's got to come from some other air cleaners. Let's talk about those devices. Quick takeaway before we get into them. ASHRAE recognizes that you first have to follow the ventilation rate procedure. That's really important because that handles contaminants like CO2 and VOCs. This is not an outdoor air reduction strategy at all. It is about a supplement to the existing ventilation. Meeting this requirement requires controls beyond the minimum ventilation. That's the other point, which I think is key, is that ASHRAE acknowledges that the regular ventilation rates that you would follow under 62.1 as an example are not sufficient for managing virus spread or aerosolized infection spread in a building. That, I think, is a very critical point. This is the first time ASHRAE has taken a position on air quality that has said that the ventilation rate procedure is insufficient for this particular problem. I think that's a pretty exciting point. So our question is, if that's true, and we think about the long term, as building requirements start to change and include this, how do we balance cost complexity in this? It's clearly not more outdoor air. There's a lot of cost associated with that. So what do we use? And so we're going to get into those details in a second and talk about those trade-offs. We'll get up to quiz question number 2. Ryan, you want to make it live?
All right, you can now answer number 2. By the way, the correct answer for number 1 was C. I shared that. I don't know if everybody can see it when I share. That's why I'm mentioning that. And I'll do the same thing again after this one's done. I'll share the results and you'll be able to see the correct answer.
Excellent. I still can't participate. Okay. Hopefully you guys are doing well on this one. So
I don't know, Seth and Sal are answering them all correct. It's just you. You're getting them wrong. I don't know.
This guy. All right. Thank you. So let's talk about effectiveness of air cleaners, and this is where we're starting to add up those volumes of equivalent clean air. So the safety and effectiveness of an air cleaner needs to be evaluated under the standard. And to repeat from before, it includes ultraviolet, electrostatic discharge, ionizers, photocatalytic oxidation. All of those systems would have to be evaluated to Appendix A of the standard. So we apply the established standards that are in that appendix against these products in third-party labs. And so this is the framework, the structure that ASHRAE set up as a workflow to get products approved. These results have to be extrapolated to real-world conditions. One of the challenges that we all remember from the pandemic is that there was this conversation about the shoebox test. Like, hey, my device worked really well at killing COVID in a box this size. Yeah, but what about real world? And so ASHRAE addresses that by saying that your performance needs to be scaled to real-world applications. And then from a safety perspective, I mentioned the word byproducts. I mentioned them earlier, but what is embraced in 241 is that UL 2998, which is an established third-party test for ozone emission, needs to be evaluated on each product. ASTM whatever 8407 is to evaluate formaldehyde generation. And then ISO 14644 is for particle concentration measurement. So we'll get into these in more detail, but just understand that there's effectiveness and safety that are tested in the same application. And that safety testings are looking at the critical byproducts that have been used to, I'd say, discredit or challenge air cleaners and their effectiveness in the past. There are air cleaners, I'll just spend this time right now to say it. There are air cleaners that are used in certain applications that are that clean the air through generating ozone, and ASHRAE is distinctly against using ozone, and so that's why that test is so important. UL 2998, the threshold for ozone is 5 parts per billion. Just to give you an idea, it's a very, very low threshold, or difficult to pass. So anyway, so effectiveness and safety testing need to be performed using identical operating conditions. That is a huge point. So you can't set your device to be effective at zapping all the bugs and then you turn it down to pass safety because you just turn down all the ozone generation. So ASHRAE says, no, that's not allowed. You have to set it up and set it the same way in both cases. The testing needs to be done in an independent third-party lab. There's only about 4 or 5 of them in the US. The chamber volume needs to be at least 800 cubic feet. So it's not small, but it's also not huge. The bigger the chamber, the better in this standard, by the way. But 800 cubic feet is much larger than a shoebox. Air cleaners need to be operated per the instructions of the air cleaner, which makes sense. Triplicates of each test need to be done with the cleaner on and the cleaner off so that you have a base case to look at net reduction. Then you look at actual reduction, the sum of the device on and how effective it is at removing the particles or the pathogens. The average of the runs is taken, not the best case. And then the effectiveness testing should be done with something called MS2. MS2 is a bacteriophage of E. coli. It is selected because it is safe and not tied to a specific pathogen, so it allows you to do the testing in cheaper chambers. You can do a biosafety lab level 2, not a level 3, so it's a little bit less expensive. And in the standard, to both our surprise and pleasure, it says the air cleaning manufacturers are also encouraged to test against specific pathogens to determine more specific claims. If you think about that, hey, you used air cleaners for a particular coronavirus. There's also influenza and other things that people ask about. So how does your technology work on MS2? How does your technology work on coronaviruses or influenza? A particular manufacturer can go do this exact same testing protocol and deliver results against MS2, against influenza, against coronaviruses, you name it. And so you as a designer can look at those values and determine the equivalent clean air delivered against certain pathogens, and especially against the ones you care about or the customer's asking about. Remember, the math here is in triplicate, so you actually see 6 lines on the chart. The reason you see 6 lines is you have 3 control runs. You have 3 runs with the air cleaner turned on. And keep in mind that the value here is not in the point where you end at the end, it's the slope of the line. So how effective is the device at removing pathogens in that window in time? And the more you remove in that chamber in the shortest amount of time, the higher value you get. I want to make this point. If you guys think about it, take a minute and say, hey, you know, in 2021, 2020, every cleaner I talked about had 99% removal. If you think about it, everybody said, hey, my device does 99. Pretty much everybody said my device does 99, or my technology or my chemicals do 99% removal. That may be true. The question we should ask is, over what period of time? Because SARS by itself is 99% effective after about 2.5 to 3 hours at killing itself off. It has a very short, relatively speaking, a very short life. And so the question is not whether the device gets to 99, it's how effective is it at treating the pathogen in a period in time, an early period in time. Imagine the scenario. Hey, I'm happy with a device that kills 99% in 2 hours, but the kid next to me in class just sneezed. So do you want to be exposed for 2 hours, or do you want it to be effective in 5 to 10 minutes? And that's why this slope is so important. The higher the slope of reduction, the steeper the slope of reduction, times the volume of the chamber, as you can see here, delivers more clean air. So our takeaway here is that standard 241 really does raise the bar for air cleaners. Number one, you got to go spend the money to do the testing. Number two, it's done in a lab that's independent third party with repeatable results. So you as a design engineer can look at those results and say, now I know this thing works at least. It closes the common loopholes of people doing their own claimsmanship of their own products. And in the end, you can evaluate whether the air cleaner delivers a volume of air that's relevant or effective for the space that you're using, because it is scaled to a real world population. So let's look at quiz question number 3. Ryan, there you go.
Should be able to answer it this time. I think I fixed it.
Oh, all right.
So now the pressure's on.
It did work.
It doesn't let me answer it though. So I don't know.
It says, thank you for your participation. I'm a participant now. I did feel
As a
very
reminder,
active.
everybody else, type your questions in and we'll get them addressed here.
All right, that one should be pretty straightforward. Let's get to the next one. Let's get to the next section here. So what do you as an engineer get? So all the manufacturers have to do all this work, go to the labs, do all the evaluations, spend all the money, so forth and so on against this standard. So what do you get as a result? You get an independent third-party lab test report. You probably get a manufacturer saying something on their website or on their spec sheet that says 241 compatible, compliant. The only way you can prove or know that that's accurate is to ask for a test report. In that test report, you should identify that it is a third-party lab, one of the 4 or 5 third-party labs that exist. You should see a description of the chamber. You should see the size of that chamber, the surfaces should be stainless steel, how the equipment is configured. So it's a pretty nerdy kind of thing to dig into, but it's really interesting if you want to spend the time. The other thing that's added in the test report that was it's not required under the standard, but it is required under the test report, is how noisy is the device. I think it's really interesting. One of the things that we've heard from customers in the field is, hey, I installed these, or I brought these air cleaners into the classroom, and they're like at 45, 50 dBA, they're noisy. They didn't say 45 dBA, they're just too noisy. So we unplug them, or we turn them down to low level. Well, okay, but is that HEPA filter running at low level effective at cleaning as much air as you need? I don't know. And so looking at the noise level at the performance level is helpful as an engineer to know what the likelihood is of a happy customer when it's installed, which I think is pretty cool. And the other thing that's required under the testing report is if you are a UVC product, it needs to be evaluated against the electromagnetic radiation levels. So the intensity of the field plus the UVC wavelength is evaluated. So just from an education perspective, on the right-hand side are pictures from some lab reports from some different manufacturers to give you some details. On the left-hand side is kind of your rules of thumb. Number one, you got to make sure it's triplicate test. The average of 3 results are used, not just the best result. The chamber's got to be large and it's got to be documented. You want to understand the lab equipment being used has the sensitivity required to measure the removal values to the degree that you need. So, if it's a plus or minus 1% and you're making a claim at a 0.5%, clearly the equipment doesn't support that claim. Chamber performance. This is really important, folks. I know you probably have never spent the time on this, but we do. The temperature in the chamber and the relative humidity in the chamber should be consistent from run to run. Temperature up, humidity up has a very different performance on aerosolized particles and pathogens than if it's held the same over and over again. That makes it much more interesting to understand. So you're looking for something within 5% from run to run. It also shows that the lab has control of their chamber, a really important evaluation question. All modes of an air cleaner need to be evaluated if you're going to recommend it. I have seen test reports of 3 products with 3 different operating modes, high, medium, low. They only tested high and medium, and they forgot to test low or didn't test low. There could be reasons why they didn't test low, and there could be reasons why they didn't spend the time and money on it. But the product is capable of doing high, medium, low. As an engineer, are you comfortable with that? That's your choice. And then remember the ACS, the volume of air cleaned air, is the slope of the line. There's a calculation to do so. You see it on the right-hand side. It looks at the natural decay rate. It looks at the decay rate with the air cleaner turned on, multiplies times the volume. If it's just 99% after an hour, that's not the way it's supposed to be done. Safety report. The safety report is super important. As I said before, if there was one takeaway I'd encourage everyone on this call to be thinking about is if you're looking at air cleaners on a project, you want to make sure at least, even if you're not doing it for 241, you're not doing it for aerosol, I'm just doing it for odors, I'm doing it for particle issues, I'm doing it for wildfire smoke, whatever it is, okay, that's driving you to use an air cleaner, or even coil cleaning, fine. The question you should ask yourself is, does the product at least pass the safety threshold? And those safety thresholds are on the screen here. They're actually part of the standard. Formaldehyde. Formaldehyde can be measured, and it needs to be less than 50 micrograms of generation per hour, okay? The equipment that does that measurement needs to have a test detection limit of less than 0.5 part per billion in a 1-minute sample. That's a very specific piece of equipment, by the way. There's only one manufacturer of that equipment. They're very expensive pieces of equipment. The labs have them, okay? So it is possible to do the work. Ozone generation needs to be less than 5 parts per billion. That is the UL standard. And then particles. There's an interesting spec. The particle test must indicate that you don't generate enough particles to move past only one ISO band for cleanliness. So I know this is a lot. There's a lot to process here. But I'll pause here. Here's a question Jerry asked. Does the standard address the effectiveness of air cleaner over its lifespan or give a lifespan of air cleaning equipment? Really great question, Jerry. No, it does not. One of the things that it does mention as part of the building readiness plan or that IRMM is the equipment needs to be maintained. Filters need to be replaced. Things need to be, whatever it is. If it's a UVC lamp, it needs to be maintained in some interval. So it says in the standard, you need to address what preventative maintenance measures need to be used to make sure the equipment is in good working order, but does not talk about its effectiveness over its lifetime. It does address, though, and I'll get to it in 1 second, does address filters and their performance over their lifetime in a little bit, but nothing around the air cleaner. It's a great question. The expectation, obviously, is that it works as well day 1 as it does day 5 or 6, or year 5 or 6. That's not always true. And so, we think about cleaning, maintenance, management, replacement bulbs, parts, filters, all of those things become an important part of the conversation, but it does not address them. Great question. By the way, Jerry, if I had my choice, I would love to be able to profile these devices in some different operating conditions, not just this chamber with this one particular particle. Anyway, so the lab reports are what you get as an engineer. or they're available to you as an engine to review. They look at the effectiveness and the safety. The questions that you should ask is the test report complete? Is it really installed the way it's meant to be installed? Is it in a recirculating duct? Is it supposed to be in the middle of a room? How am I supposed to organize the device for effectiveness? Does it make sense that the way it's organized in the lab test is the way it would be used in the field? It's a good question. Is the testing report adequate and clearly repeatable? So does the lab have control of their chamber? It's a good question. And does the safety and performance testing match the desired operating mode like I described? Question number 4. Here we go. It's on the screen. I'm going to take a minute and answer it. All right, let me move on. We need to spend some time on filters. Filters are a very important part of the calculation, as you'll see in a second. And I am watching the clock. Starting in January of 2025, only A-rated filters are appropriate for the use under the standard. I'm making that point first. But the first point is that any MERV filter, any MERV rating filter below an 11 is not considered as part of the standard. Why is that? Because the particles that we're talking about that pass through the airstream that infect us are smaller than what a MERV 8 is very effective at removing. They have very low removal values on a MERV 8 filter. MERV 11 and higher starts to become meaningful with the removal values. And so their effectiveness ratings only start on MERV 11s. MERV 11A will be required as of January 1, 2025. What is an A-rated filter? An A-rated filter, to the question we had earlier, an A-rated filter to the question we had earlier is a filter that is discharged and then evaluated. If you guys aren't familiar with this, filters, when they're first manufactured, have some static charge on them. That static charge loses its effectiveness over time, but a initial brand new product tested in a 52.2 chambered sort of 52.2 test, an ASHRAE 52.2 test, will have a better removal value on day 1 than it will on day 30 or 40 after it gets a little bit of loading on it, moisture, other things that drop off that static charge, okay? So MERV 11A, you actually discharge the filter through a salt spray, whatever evaluation, clean it off, load it, and then run it. So this is the removal value just on the mechanical properties, no electrostatics. That is what's required starting 2025. Why is that interesting? Because we know MERV 11 filters today, when they go through an A rating, will actually have a lower performance. But a MERV 11A will have MERV 11 performance even after electrostatics disappear, okay? Hopefully that's helpful. Filters are very straightforward. If you look at the standard, there's a lookup value, and you'll notice below 11, there's a 0%. But when you get to MERV 11, you get a 60% removal value. For particles, these aerosolized viruses, you get a 60% removal value for all of the air that gets recirculated through a MERV 11. So now you can start doing the math. Okay, if I have this classroom with 400 CFM of outdoor air, maybe 1,200 CFM of recirculated air, 1,200 CFM times 60 is a source of cleaned air, VACS. So now maybe it's coming together for you that says, hey, I've got an air cleaner, great, but my primary air cleaner under this standard is my filter. Now, we can ask questions all day long whether the virus or the particle that's in the breathing zone makes its way all the way up to the filter that's on the roof of a building. I don't know, but the point is that you do get credit for it under this standard. Oh, I should have made the point. You'll notice different levels of removal value. HEPA is at 99. Okay, so all the air that makes its way through a HEPA filter is essentially clean when it exits a HEPA filter under the standard for infectious aerosols. Okay. So number 1, ASHRAE recognizes filters are a substantial contributor to aerosolized pathogen reduction. I'm going to put on a little bit of a skeptic's hat here, or maybe a balanced view on this. Keep in mind that the pathogen used here, or the pathogen or the particle mix that's used for that MERV rating for 60% removal is a mixture of small and medium and ultra fine, medium, and slightly larger particles. That mix gets you a 60% reduction. The pathogen itself is actually very, very small. But the assumption is that you use the pathogen that's actually wrapped in mucus or in water droplets, so you get the larger sizes, which is why you rate filters to a slightly higher result than would normally have been the case for these small particles. To give you an idea, that's the justification that ASHRAE put together in these filters. I'll also just say on balance that filter manufacturers and the idea that a MERV 13 plus typical design would meet the requirements of 241 is aligned with what happened during the pandemic. If you remember, at some point we settled on MERV 13, 6 air changes per hour. You do that, and in most applications, you get the VECAI, or the volume of clean air that you need. Okay? I jumped ahead to the answer, but now you know it. My only other point here, as you guys know, if you specify high performance filters, due to the cost and the issues associated with them, availability, maintenance, whatever, will the owners continue to use the right filters? That's always a question that we get asked. So we'll go to quiz question number 5, and then we'll get on the slope to completion here. Oh, it's a good one. Hopefully you guys can get that one pretty quickly. Let's go to the really detailed stuff. Okay, so now we've looked at air cleaners. We know that the air cleaner third-party lab report gives you a number. We've looked at filters. We know the filter rating gives you a number. So let's put it all back together. So remember that formula from before. So VACS, or the volume of cleaned air. You can add in, again, outdoor air plus filtered air plus air cleaners to come up with a number to see that if it's greater than if you look at the far right, that VECAI, that's the total volume required. The good news is there's a calculator. Sorry, there's a calculator for this. Makes your life easier. So on the left-hand side, I have a basic design, and then I've had some different scenarios put together. And so we'll just be able to evaluate them pretty quickly. And let's jump into it. I have a hypothetical classroom. It's got 1,500 CFM of supply air. So that's what the system is, the equipment is rated for. It has 444 CFM of outdoor air, 33 kids in this classroom. That is a MERV 8 filter. So what do we know about MERV 8? 0. Has a 0%, you can see the 0% removal value. So epsilon PR is what they use to describe filter removal. So it's 0%. I have no natural ventilation. The windows are closed, and there's no air cleaner added. Under MERV 11, you see on the right-hand side, you take your, so it's 0. So let's just say, let me go back to it. Column number 1, the existing design. The MERV 8 filter gets you a total equivalent clean airflow of 444. You guys are doing the math at home, you know that 444 is the outdoor air alone. Okay, so then I say, all right, that didn't meet my requirements. Let me add a MERV 11. My owner will definitely maintain with a MERV 11. That gets me a 60% removal value on the recirculated air. And so you see the recirculated air math results in 634 VECAI. So I got 444 of outdoor, 634 of recirculated cleaned. That gets me to 1,078. Divided that by the 33 kids, and I've got 32.4 CFM per kid. Still don't meet the requirements. Remember, I'm aiming for 40. 40. So I kept the MERV 11 in the design. I've tried some different permutations you can see here. I went to a MERV 13, it didn't pass. You add a MERV 11, keep your MERV 11 in, and you add a cleaner that delivers 275 CFM of cleaned air, I'll meet the requirements. So imagine, basis of design, I've got my outdoor air where I want. I've got a MERV 11 filter, which is a good, responsible choice, let's just say. And in the case of an IRMM, I either roll into the room an air cleaner, or I plug in, or I'm using it all the time. If it's a passive type technology or one that could be remotely controlled or is just very cost effective and runs all the time, I can always deliver the air I need to meet 241. From a budget perspective, it may not be very painful. That's just something to consider. Let's look at the next scenario. This is call it a doc in the box or dentist's dentist office waiting room. Okay, this is probably the most disturbing scenario. If you look at the bottom, the equivalent clean air, I should say I'm sorry, look at the top. The target ECAI, so line 5 in the chart, has a room requirement of 90. You're supposed to deliver 90 CFM per person. because this is a known space where sick people congregate. And so the idea is in these spaces in a healthcare waiting space, you need a lot of clean air. If you follow the minimum requirements of this space under the ventilation rate procedure with a MERV 13, because you as a designer knew you needed something with their 77% removal value, you really only deliver 50 CFM per person in your basis design. You're trying to get to 90, you almost have to double it. And so I went to a HEPA filter. Some of you probably should be rolling your eyes like there's no equipment that supports a HEPA in these types of applications. Okay, I get it. But just theoretically, I had a HEPA and I still don't make the math. Why? Because I've got 30 people in this space and I'm trying to get to 90 CFM. This is one of those scenarios where adding 4 air cleaners and doing all seems unreasonable. So really, the IRMM for this application is put half the people in their cars in the parking lot until the waiting room opens up a little bit and let them in. If you guys remember what happened during the pandemic, they're like, they made you wait outside until the population was lower or there was room for you to sit in there with spacing. That is the answer according to the standard. And I think that's, as an engineer working with an owner on this question, is if you start to get really out of control around all this extra air cleaning, the answer may be, hey, during an IRMM, hang a sign that says, max population 20 instead of 30. Hopefully that's helpful. So then let's go to the wrap up here, right on time. So we've talked about MS2 a little bit. Let me spend a few more seconds on MS2 since the slide reminded me to do it. Opinion range here is MS2 is an interesting choice. It's a pretty poor surrogate because it doesn't transmit through the air the same way as aerosolized pathogens, but it was chosen for cost reasons. It's also a very, very small particle. It is a non-enveloped virus, which is one of the reasons why it's a challenge for air cleaners to tackle. So really the VEC-AI, or the volume of cleaned air on MS2, will be lower, that rating will be lower than on the types of viruses that actually make us sick, like influenza and coronaviruses. So I bring that up only because as an engineer, if you look at these test reports and you're trying to compare and contrast, it may be helpful to look at one that actually delivers on air cleaning of the things that actually make us sick. I bring that up because I think it's a really helpful point. The filter removal efficiency in the standard is based on larger particle distribution, not an ultrafine particle like MS2. As I described before, it has a lot to do with the water droplets. But my question to you as a design engineer, how comfortable are you that the water droplets or even small particles are going to make their way back to a system filter? The one thing we've learned is that you need to address the problem in the breathing zone. So as close as you can get to where the people are, the more effective you will be as an air cleaner or as a technology. Again, I bring this up because if you've done a clean room design, you look at 15, 20, 30 air changes per hour. A good classroom design getting 6 air changes per hour, you still have a lot of small particles and these viruses entrained in the air that do not move back very effectively. So again, as you just think about from a design perspective, whether a remote filter is a solid choice, that's something we would like, kind of see the standard improve. And then the last thing I'll point is that the removal efficiencies in the standard assume more idealized performance. Like I was saying, like all the air in the room, if you look at the calculator again, I'll just say it, I'll point out it assumes that all the air that's in outdoor air makes its way back to a filter and gets cleaned essentially in one cycle. So that's a limitation of an Excel spreadsheet, I would say. It's truly not a CFD design, but it's just the way the tool works. So conclusions, takeaway, and then opening for Q&A. So I'm only 3 minutes late here. The standard is here to stay. 241 clearly handles some big issues for ASHRAE. It certainly demystifies and standardizes some critical tools for indoor air quality. And we would expect, and what the committees have told us, is that the requirements of 62.1 and 62.2 and 170 over time will roll into this idea of equivalent clean air for infectious management. And so you will see this idea of the IRMM and 241 and equivalent clean air rolled into the existing base standards for ventilation. 241 is a huge step forward for our industry. It's a year going on. We get asked about it all the time. It's not currently required by code anywhere, but it is a criteria that you as engineers can use to evaluate at a minimum the safety of air cleaners. The standard is under continuous maintenance. We are aware of some testing standards that are continuing to be updated because labs have struggled with meeting the requirements of the 241 testing. Believe me, we know firsthand. But they are working on that. There's a meeting in Indianapolis coming up with ASHRAE where some of the committees will be reporting out some additional changes to the testing standards in the 241 standard. And then the final takeaway is that air cleaners are an important engineering tool that we want to help achieve more confident, widespread adoption. So that we wholly and fully embrace this standard. I think the one final point I would make is that, and I get asked this question, so I'll just go ahead and put it out there before you guys hit Q&A. Is anybody adopting it? Two things. Number one, the National Institutes of Technology have asked the GSA, that's the landlord for the government buildings that aren't military, to build some spaces to 241 and evaluate that cost of it. So that was recommended about a month ago. So we think we know the GSA will pursue 241 construction projects in the coming year. And also Ontario, the province in Canada, is evaluating whether they would make 241 a requirement for all of their public schools. The last thing I'll say is that in some experience with specific commercial customers, let's say, that deal with a immunocompromised population. So think of people that go to dialysis clinics. We've been specifically asked by those folks how they handle this because they consider their building to always be in an IRMM. So there's a set of customers where a focus on this removal value and the amount of clean air required makes sense, and they ask their engineers and their designers, what does ASHRAE recommend? And now you know where to go. It's in standard 241. And I'll pause there. That's it. Do you guys have any questions, comments, any other feedback from me?
There was a couple people with their hand raised. I don't know if they raised it because they clicked the wrong button or if they wanted to ask a question, but I could unmute if I can read the name. Sama Sundarama. So if you did have oh, maybe I can't unmute you. Oh, there you go. So you're unmuted if you had a question. The other one was Mike Melody. You raised your hand. I don't know if you had a question, but you were unmuted if you wanted to ask it. And of course, anybody's welcome to type questions in as well. While we're waiting on that, I'll just mention, obviously, Audie did a real good job following all the ASHRAE type rules for presenting and didn't talk about any products or anything, which is what we have to do for PDHs. But as you probably are aware, he does work with GPS, as does Seth. We've been using GPS for several years now. We used them actually probably 10 plus years ago, and then started again ramping it up when COVID happened. And it is a company that we work with that has a lot of technologies to do some of the kind of stuff we're talking about in the standard here. So if you have questions on that, you can reach out to them. You can reach out to me. You can reach out to Sal. You can reach out to your territory manager, and we'll figure out what answers you need from that perspective. Mike typed his question in. I don't know if you can see it there, Audie, or I can read it for everybody. Does 241 address scalability? I would compare this procedure similar to using dynamic reset or DCV. For a fixed outside air calculation. Seems like scalability would eventually need to be considered as DCV was applied to the standard OA calc.
Yeah, no, that's a really good point. So it's almost like one device is good for, if this one device was good for 400 CFM of cleaned air, and I put it in the roof of the building, do I get 400 CFM in every space? No, you just get 400 CFM as a quantum, as a unit. And so that's where applying the product that says, hey, this air cleaner is good for 1,000 square feet space or 1,000 cubic foot space, delivers 400 CFM. That's really the way to think about it, about how to apply it. So as you think about the reset or, using an air cleaner to purge a space before people come in, I think that's an interesting application. It's something that could be done very effectively. But one of the things that demand controlled ventilation is based on, I'll answer your question about that as well. One of the things that demand controlled ventilation is really based on is CO2. And so CO2 often drives the demand controlled ventilation question. which does reduce outdoor air. So if you have an IRMM and you have a demand control ventilation strategy, you're probably going to a place where demand control ventilation gets disabled. You want as much outdoor air as you can get and your system can process, and then you bring in the other mitigating technologies. So DCV is allowed. Remember, so DCV is allowed under 62.1. And so if you use demand control ventilation under 62.1, if your demand control ventilation strategy is to reduce outdoor air, you got to take that into your consideration around 241. Hopefully I'm answering your question, Mike, because what you really want to do is make sure demand control ventilation goes to zero, or essentially as much outdoor air as you can get to drive that in, and then you add your other mitigating technologies on top. Good questions. You're the first person to ask me about demand control ventilation in this topic, but it is appropriate. It's very appropriate to consider. Good. Well, I'm not hearing any other questions. I'm really thankful for the attendance. You guys, really good attendance from the team. I really appreciate the opportunity to present. We will get these slides out. I'll turn them into a PDF, and we'll have maybe Ryan will send them out to all the folks invited. That sounds good. Thumbs up. If you have any specific questions, my email is acash@gpsair.com. It's pretty straightforward, acash@gpsair.com. If you have any questions about that deck, and I'm sure Ryan will copy me on the send on that. If you have questions about the deck or you just want further information, please reach out to Seth or myself or Sal or anyone in the TEC organization. Would be glad to help out. But thank you so much. And Mike, are the worksheets for some of the calc shown? So the worksheets, I believe I can send the calculator. So this is the last question, and we're out of time. I believe I can send the calculator. Let me double check what the ASHRAE rules are on that, because it's not one that you buy. I'll send you a link. Yeah, it's not one that you buy. I think it's free, but it was limited distribution. If I'm allowed to send it, I'll send it. Okay, I'll just double check that today. But yeah, and you can play with the calculator all you like. Thanks, everybody.
All right,
I really
thank you, man.
appreciate it.
Appreciate it.